2.2. We have 4 objectives. We're going to get through maybe 2-ish today. We are going to describe and apply the 68, 95, 99.7 rule, describe the standard normal distributions. We'll eventually work a little bit more with performing normal distribution calculations and assessing normality. That's like a day completely of its own. First things first, normal distributions. One particularly important class of density curves are normal curves, which describe normal distributions. So a normal curve is a symmetric, single-peaked, bell-shaped curve. A normal curve, it's symmetric, single-peaked, it's bell-shaped. What happens is we have this mu, your Greek letter, is your mean. It's always going to be in the center, and it's always going to go to your peak. So here's your mean, and then we have the standard deviation that goes on either side. And they will look slightly different, but the mean and your standard deviation is specifically what's going to define your curve. So normal distribution, like I just kind of said, it is described by a normal density curve. It's described by a normal density curve, and we abbreviate it as this. You're going to see this written all the time. N, and then in parentheses you have mu, comma, sigma. And make a note, mu stands for your mean, and sigma is your population standard deviation, your standard deviation. So we had kind of talked briefly 2 days ago that sometimes our data is so nearly symmetrical, so nearly fits like this perfect curve that we can put this smooth curve over it. Specifically, today, this one has a name. If it's perfectly symmetrical or nearly perfectly symmetrical, that's called our normal curve. What do we do with them? Why do we care? Normal distributions are good descriptions for some distributions of real data. So sometimes you're going to have real data. It's like this curve totally fits it. And other times it's used for approximations. So sometimes it's like, this is what we've seen in the past. We're going to use it to approximate what's going to happen in the future. And we use it for statistical inference, so that we can infer what's going to happen in the future. The 68, 95, 99.7 rule, you'll sometimes hear it referred to as the empirical rule in different textbooks, but I'm going to say 68, 95, 99.7. What happens? 68% of the data fall within one standard deviation of the mean. Abbreviated. 68% of the data falls within one standard deviation of the mean. So like right here, this is my center, this is my mean at 0 here. So if I go left, a standard deviation, if I go right, a standard deviation. In between these 2 points, this is 68% of the data. 68% of your data would lie in that range. And then we have 95. Approximately 95% of the observations fall within 2 standard deviations of the mean. So from here to here, this is 95% of our data. And then we have 99.7. 99.7% of the data fall within 3 standard deviations of the mean. So from this part to this part, this is 99.7. Remember that example where we were talking about the batting averages or the home run scores for our, like Babe Ruth and all those guys? And we had some people who were at 4 and 5 standard deviations above the mean. That was like their Z-score. And I told you that's completely unheard of. Why is it like completely unheard of? Because look here, 99.7% of the time, all of our data is going to fall within 3 standard deviations of the mean either way. So if we have somebody that's 4 or 5 standard deviations above the mean, that's clear out here, and the chances of that happening are slim to none. So between our 3 standard deviations is 99.7% of the data. We still have some in these tails here. So you do have to be careful about that. There's still some extra percentage beyond your 3 standard deviations. What is that? Well, if we have 100% under the entire curve, 100 minus 99.7 leaves me how much between both of those? So 0.3% divided by 2 gives us 1.5% in here, or 0.15%, I'm sorry. 0.15% here and 0.15% here. Does that make sense? That gives us 100% total underneath the curve. So here is an example. The distribution of Iowa Test of Basic Skills vocabulary scores for 7th grade students in Gary, Indiana is close to normal. Suppose the distribution is n 6.84, comma 1.55. What does this 6.84 stand for? This is our mean. It was like your mu. And this 1.55, this is our standard deviation, which is your sigma. That's what those numbers represent in those parentheses. So sketch the normal density curve for this distribution. What is this going to look like? Here's my x-axis. In the center is our mean. So my mean was 6.84. And then I'm going to count up 3 standard deviations. I'm going to go 6.84 plus 1.55 and see where that gets me. Calculator trick, ready? Here's a shortcut. If you type in 6.84 and push enter, it kind of like locks in that number, and then push plus 1.55, push enter, push enter, push enter again, it adds it on those 3 times real quick for you. So let's jot those numbers on our curve here. So if I add 1.55 to that, I get 8.39. Then we're at 9.94. And then we are at 11.49. And I need to go in the reverse. I need to subtract. So 6.84 minus 1.55 3 times. Lock it in, go minus. Get your 3 numbers, put them on your graph. Alright. Here's the scientific way of how we make our curve. Am I going to expect you to do this? No, we're just going to sketch it. But the mean was 6.84, so that's going to be our peak. On either side of that, to figure out where the next point goes to make our curve, we're at 60% of the height of the first one. So if I'm like, well, this is roughly the middle, if I go up about 60%, I'm going to put a dot at my first standard deviation and reflect it. So this is like 60% of the height, and then the next one, I look at this first standard deviation, I want to go a quarter of that height. So I find the middle, like halfway in there. Here's where my next dot goes. Try and line it up exactly. And your third standard deviation is just barely above your x-axis. So I put a dot like right there, put a dot like right there, and then we connect it with smooth curve. Oh, it's beautiful. Look at that. Cool? Alright, so there's your curve. Part B, what percent of ITBS vocab scores are less than 3.74? Here's 3.74, and I'm just going to kind of shade this in here. I'm interested in this part down here. I want to know what percent of the data is that. So here's where we kind of go in and we start dividing and conquering and seeing what we know. This is my mean in the center. So from 3.74, this is 2 standard deviations below. This is 2 standard deviations above. I know in between these 2 points, 2 standard deviations is how much of my data? 95%. There's 95% of my data. So how much is going to be in each of those tails? There's 100% total. Subtract 95%, that gives me 5%, but that's for both of them. 2.5. Divided in half, this is going to be 2.5%. And the other one would also be 2.5%, so it still adds to 100. So in part B, we have 2.5%. What percent of the scores are between 5.29 and 9.94? I am going to undo this to get it out of here. Let me go even a step back. Between 5.29 and 9.94, I'm interested in this in here. So, divide it up. What do we know? The first standard deviation is 68%. And then what? I've got this extra part here. This is my second standard deviation. The second standard deviation is 95%. So here's 68%. How am I going to find out what's in either of those? 95 minus 68, that gives us 27. It's 27% for both of those. To find out how much one is, divide it, we get 13.5%. So this part is 13.5%. Yes. So here's 68. You have 13.5 more, so 68, 13.5. We add them together. We get 81.5% of the data lies in between those two values. Let's do this. For some reason, this question is forever tripping everybody up. I know you guys don't have a lot of room on your paper, but let's do this. Here's your rough sketch of your curve. We have 0, and then I have 1, 2, 3 standard deviations above, -1, -2, -3. I know you guys can figure out this math. Some people, it'd just be easier if I show you this. Between my first standard deviation is how much of the data? 68%. So how much in each of these? So this is 34% and this is 34%, right? What I'm trying to get at here is I'm trying to show you how much is in each of these portions. So between my two standard deviations, that's 95%. So I want to figure out how much is in this one and how much is in this one here. So what do? 95 minus 68, that gives us, what do we say, 27? Divided by 2 is 13.5. So I have 13.5% here, and I have 13.5% here. If I added all four of those numbers together, that'd give me my 95%. Right? And then my third standard deviations is 99.7%. So how much more am I gaining between these sections on the end here? So you have 99.7 minus 95 gives us 4.7. We divide that in half, and this section is 2.35. And this one contains 2.35%. And we had talked about this one earlier. If between these three is 99.7%, how much is left for the ends? 0.3 total. So this part is 0.15, and this part is 0.15. To have that detailed out, I'm 99% sure that's going to benefit you, so that you have that diagram on your notes. You need to know what percent is in each of those. And I think it'll be a quick way to look, because if I say what's in between this one and this one out here, you can take 34 plus 34 plus 13.5 plus 2.35%, add those together real quick, and that'll get you your... The 0.15? It's 100% completely under the curve. So if that's 100%, what's the difference between those two? 0.3. Divide that. So it's 0.3 for both of these ends past our 3 standard deviations. 0.3 divided by 2 gives us 0.15 on both ends. Cool? Okay, you guys try the next batting averages example. A, B, and C. This is not right. We have 5% for each end, divide by 2. That gives us 2.5%. Oh. Between 2 standard deviations is 95%. And so what's left? There's 5% between both ends. Divide that in half. This is 5 divided by 2 gives us 2.5%. And here's where we're going. For the sake of time, I'm reworking that assignment sheet completely for this lesson. Page 131, 41 through 46, it's basically this exact same content for tomorrow. Okay, sketch your curves, figure out what percent lies in between different standard deviations.